Strategy for solving related rate problems. First, you want to read the problem carefully, generally at least twice. Second, you want to draw a diagram or a picture. It helps you see what's going on. Third, you want to assign variables to all quantities that are changing and label all constants in the picture. Very important, we're going to talk about this, but once you have the picture, it helps to kind of figure out what's going on. Next, you want to write down the givens and the wants in mathematical notation. These will likely include rates of the form of this. If you notice, these are all derivatives, right? That's what a rate is. It's a derivative. So dHdt, drdt, if you notice, are also all over dt. That's because in related rates, what we do with respect to time. We're talking about a rate here, so it's over time, some form of time. So it's always going to be one of those. When you talk about a rate, how fast, how much is it increasing, it should be a rate. We can also add, don't forget to add the constants like x, r, and h. Sometimes they're constants, sometimes they're variables, so you gotta watch out. Right, general primary equation that relates to variables. It is called related rates, so we want to relate the variables. This is where your formulas come in, your area formulas, your trig formulas, all that good stuff. If any quantities in the equation are constant, you may replace the variable with the actual number. Again, that's only if they're constant. That doesn't happen very often. When they're constant, it makes life so much easier. It makes it a much easier problem. But most of the time, like we said, you can leave them as variables. You would need to use geometry. Sometimes you can need to use geometry manipulate the formulas. Like you can have more variables than you need, and we like move around stuff. We'll see that more in the next video. Once you do all that, you can use the chain rule and implicit differentiation to take the derivative of both sides of the equation with respect to time. Always with respect to time. And then once you have that, you just substitute the given data and solve for what you need. After that, just round your answer and make sure it makes sense. So let's do an example. Example 1. The size of a square increased at a rate of 2 inches per minute. And our first question here is how fast is the area of the square increasing when the sides are 3 inches. So let's kind of go over that again. The size of a square increased at a rate of 2 inches per minute. So we're talking about a square. So let me draw it. We have a square. We know squares have 4 right sides and 4 congruent angles, but we just go to the sides for now. We know sides are increasing at a rate of 2 inches per minute. So this is label a side. You can make it anything you want. We'll say S. And it's the sides are increasing at a rate of this. So my side's increasing at a rate. So remember, it's a rate, so that's ds dt, because my side's increasing at a rate of 2 inches per minute. So that's my first given. Right, my given is sides increasing at a rate of 2 inches per minute. It's a side, it's increasing at a rate, so ds dt. And the question says, how fast is the area of a square increasing when the sides are 3 inches? So what we're looking for is right here. How fast is the area increasing? Notice it said increasing, so another rate. We're talking about the rate of the area. So that's going to be dA dt. That's what we want. I want to know what dA dt is. How fast is the area increasing? When the sides are 3 inches. Now here's the thing. When s equals 3. That's not a constant. Our sides are increasing, so they're not constant. This just says when the sides happen to be 3 inches, how fast is it increasing? So it's something we're going to plug in after we do our work, not before. This is not a constant, so we'll plug this in after. So the next thing we got to do, right, we have a graph, we have stuff labeled what we want. Let's try to relate these two things. I got to relate a side of a square with the area of the square. Well, there's the formula that should kind of go with that, right? How do you find the area of a square? Area equals side squared. Because it's an area, right? You just multiply the side times the side, so you get the area. That's our equation. Alright, once we have our equation, we can plug in any constants. I don't actually have any constants. Area is not a constant. Sides are constantly increasing, that's not a constant. So all we do now is take a derivative. We take d of dt to both sides. That's implicit differentiation. Derivative a is just 1, but the wrong variable. dA dt equals derivative s squared is 2s, but the wrong variable. ds dt. Right, some implicit differentiation. And now we just plug in what we have. Right? I have ds dt is 2 inches. Almost plugged in for the wrong thing. It goes here. I have s is 3 inches, so that goes in for s. And I'm looking for dA dt. So I have this. dA dt equals 2 times 3 times 2, also known as 6 times 12. Now I gotta have my units. So it's actually fairly easy, but let's talk about this in general. What did I find? I found the area. Right? So actually I found the rate of area. So area by itself is inches squared from my inches, but it is the rate, so you're not gonna divide it. It has to be a fraction, so you can divide it by minutes. So that's the rate just looking at the problem, what we're doing. If you want to do it really the way you're supposed to do it, well, side here was inches, and my rate here was inches over minutes. Right? So I had 2 times inches over minutes got me 12 inches squared over minutes. That's the answer. Let's look at the next one. Same idea. How fast is the area of the square increasing when the square has an area of 25? Right, so same given. ds dt equals 2 inches per minute. My want is different. I want how fast is the area of the square increasing. Well, actually, it's the same. I want dA dt. Exact same want, actually. But the other given is different. I want when the square has the area of 25. So I want this one area equals 25. Right, so let's flip it again. Not a constant, right? Area is constantly changing, size not constantly changing. We're going to use that at the end to plug stuff in. But other than that, it's the exact same problem, right? So what's our equation? Well, area equals side squared. Let's take a derivative with respect to t to both sides. d of dt. So I'm going to get 1 dA dt equals 2s ds dt. Do you notice an issue though? Oops. I want to look for dA dt, that's good. I have ds dt, that's 2. I don't have s. But I do have the area equals 25. I could use this to find my side. Right, we have this formula right here. Area equals s squared, so if I know the area is 25, it must equal s squared. Square root it. S equals plus and minus 5. We're doing the side of a rectangle, so only plus 5 makes sense. So now we can plug our stuff in. We have s, which is 5, I just found out. We have, well, 5 inches to be correct. We have ds dt, which they gave us up here, 2 inches per second per minute. So I plug that all in. I get dA dt equals 2 times 5 inches times 2 inches per minute, which gets us 10 times 2 is 20 inches per minute squared. Inches squared per minute, sorry. And that's the rate at which our area is changing. So every minute it's increasing by 20 inches squared. So let's move on to the next one. Now that our feet wet. Example 2. The radius of a circular oil spill expands at a rate of 3 meters per minute. So question A says, how fast is the area of the oil spill increasing when the radius is 45? So let's look at what we're talking about here, right? The radius of a circular oil spill. So we're talking about a circle, the radius. So here's my circle. I have a radius. And look what it tells me. The radius of the oil spill expands at a rate of 3 meters per minute. So again, notice the rate. We're talking about the radius, so dr dt. It's a terrible R. dr dt equals 3 meters per minute. And what do I want? How fast is the area increasing? So again, dA dt is increasing how much? When the radius is 45. Right, so my given is dr dt equals 3, like how much my radius is increasing. So it's increasing at a rate of 3 meters per minute. It's pretty big. I want to know how big is the area, how fast, my mistake, how fast is the area increasing. That's why it's dA dt when the radius is 45. So again, 45 is not a constant. It says, hey, when it happens to be 45, because my radius is expanding, what's the area? Or how fast is the area increasing? So we got to relate these two things. I got to relate radius with area. Well, area of a circle relates to those two. Area equals pi r squared. Right, so that's my formula. And then we always do the same thing. We take the derivative with respect to time on both sides. On the left side here, the derivative a is 1 dA dt is the wrong variable. On this side, pi is just a constant, it's just a number, so you just leave it there. So it's pi, derivative r squared is 2 r, but wrong variable, dr dt. So that's my derivative. And now we just plug in everything we have. I have dRdt right there. Plug it in. I have my radius I want. I want it at 45 right there. That's all I need. So let's plug everything in. So this will be 45 meters. dRdt is going to be 3 meters per minute. If you multiply it all together, I get 45 times 2 is 90. 90 times 3 is 270. Pi. And then we have, look at our units. Minutes and minutes per minute. Meters and meters per minute. So meters squared over minutes. That's how fast my area is increasing. So every minute, it's increasing by 270 pi meters squared, which is pretty fast. Pretty big. So that's the first problem. Second problem. The radius of the spill, if the radius of the spill is 0 at time 0, how fast is the area increasing after 5 minutes have passed? So that's a little funkier. So the radius of the spill is 0 at time 0. So when time equals 0, the radius equals 0. How fast is the area increasing? So dA dt, that's what I'm looking for, after 5 minutes. So when time is 5 minutes. Now we still have the exact same given. We still have the fact that the radius expands at a rate of 3 meters per minute. So the RDTs are given. And just like before, we got to relate these two things. Got to relate area with radius. Well, exact same formula works. Area equals of a circle is pi r squared. When I take a derivative just like last time, we get the exact same thing we got last time. So dA dt equals 2 pi r dr dt. Right, and we want to plug everything in. Just kind of like last time, there's going to be one issue. Right, we're looking for this. We have this guy. Do not have the radius though. So let's think about how we find the radius. I know the radius is 0 when time 0. And I want to know what the radius is after 5 minutes has passed. Do we know how big the radius is getting though? Like how much is it increasing? Up here. Every minute it's going up 3 meters. So at time 0, my radius was 0. After a minute, it's increasing by 3 meters, so it's going to be 3 meters. After 2 minutes, you increase another 3 meters, so it's going to be 6 meters. Right? 3, 9, 4, 12, 5 is 15 meters. So when time equals 5, the radius is 15 meters big. Sorry about that. So I'm really bad at that. Right? So when time equals 5, the radius is 15 meters big. That's how you do that. Now it's a little weird, but that's the way it works. It's like, hey, it's increasing. I know my radius is increasing at 3 meters every minute. It's been 5 minutes, so 3 times 5 is 15. So that's my radius. Gotta use some logic here. So then, just multiply all together. 50 times 2 is 6, 30. 30 times 3 is 90, 95. And then again, units, I got meters per minute, so I get meters squared per minute. That's your next related rate problem. Let's do a couple more. One train travels west towards Denver at 120 miles per hour, while a second train travels north away from Denver at 90 miles per hour. See this picture here? This one's coming in, this one's going out. At time equals 0, the first train is 10 miles east. So at t equals 0, the first train is 10 miles east, so this guy. And the second train is 20 miles north, so that's 20 miles north. Calculate the rate at which the distance between the two trains is changing at time t0. So I'm going to go a little faster on this one. So calculate the rate at which the distance between the two is changing at time equals 0. So the distance between the two is this guy right there. They have L. I'm going to change that to Z. So we want to find dz dt at time equals 0. It's a little right angle. Right? And then let's see what else they tell us. The train traveling west, this train is going at 120 miles per hour. Well, that's the rate of it, right? And if this guy is x, that's dx dt equals 120 miles per hour. And then this one going north, north to 90 miles per hour. So this guy right here, dy dt is 90 miles per hour. Now we do what we always do. I need to come up with an equation that relates to all these, because I'm trying to find dz dt. Well, it's a right triangle, so let's do the most famous one. X squared plus y squared equals z squared. And in this case, I can't put any constants in. Everything's changing, right? This distance is changing, that train's going further. This one's coming in, and actually thinking about it, since this one's coming in, right, it's going from right to left, it's actually be a negative 120 miles per hour, because it's coming inside. Compared to this one's going out, right? It's like an XY chart. Going to right positive, going to left negative. Going up positive, going down negative. And, by the way, but go back to this, z is constantly changing, right? This distance is changing. So, I just have this equation, no constants. And let's do what we always do. Take a derivative with respect to time. Derivative of x squared is 2x dx dt. Derivative of y squared is 2y dy dt. Derivative of z is 2z dz dt. We can make life a little easier. Notice that they all have a 2, so you divide everything by 2 and you just get this. So I have that. Now I gotta fill in everything I have, right? I want dz dt. So that's the guy I want. I have dx dt is negative 120 miles per hour. I have dy dt is 90 miles per hour. I want this guy, so I gotta figure out what x, y, and z are though. But they told us, right? At time t equals 0, which is what I want, what's chain at time equals 0. The first train is 10 miles east. So this guy is 10 miles east. The second train is 20 miles north. So this guy, y, is 20 miles north. And they don't tell us what z is, but we can find it. We have a right triangle. So to find z, all I gotta do is draw a right triangle. This was 10. This was 20. Let's call that c. So it's going to be a squared plus b squared equals c squared. So 10 squared plus 20 squared equals c squared. So that's 100 plus 400 equals c squared. So 500 equals c squared. So square root of 500. You can reduce if you want. It would be 50 times 10, which would be 225. It would be like 50 rad 10 or something like that. Rad 5. Anyway, let's leave it like that though. Radical 500. And then dz dt. So if I rewrite it, I'm going to get negative 120 times 10 plus 1800 equals radical 500 dz dt. That's a 600 radical 500 dz dt. Divide by that, so you get 600 for radical 500 dz dt. Remember, units, don't freak out. T is time, z is this whatever unit we're talking about. We're talking about miles per hour. So, miles per hour. And that's how it's done. So again, just to recap real quick. Right? It's all about reading the question. So one train travels west of Denver at 100 miles per hour. That's this guy. Since you're coming in, it has to be negative 120 miles per hour. And that's your rate, right? Miles per hour is a rate, so dx dt. One travels north, so it's traveling north. Again, it's a rate, so dy dt is 90. At time 0, the first train is 10 miles east, so this guy's 10 miles out. The second train is 20 miles north, so I guess 20. Calculate the rate at which the distance between the two is changing. So we want to find what this guy changed. So dz dt is what we're looking for. At time equals 0. Now I could easily change the time to like time equals 2. Then you have to do the math yourself, like, okay, wait, it's been 2 seconds, so this is 20 miles away. And then this is, so it's 40 miles away. So you start to work with, you easily change one thing to make it a little bit tougher. Right, but once you do that, you set up your equation, take a derivative of both sides, and if you have anything missing, go back and try to solve it. In this case, you use Pythagorean theorem. Plug it in, you're done. And this video is done. Next problem is a classic cone problem. It's classic in AP Calculus. They'd love to ask this type of question, so let's get into it. A conical tank with vertex down, doesn't mean it's opening down, or the pointy part's down, is 10 feet across the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, Find the rate of change of the depth of water when the water is 8 feet deep. So again, it's always helpful to read it twice. So let's go again. So a conical tank is 10 feet across and 12 feet deep. So that means we have a cone here. Tank just means like a body of water. It's a tank of water. So that's our cone. They tell us it's 12 feet deep. So from here to here, it's about 12 feet. And then it's 10 feet across. So those things are never changing. Now, 10 feet across is actually not as important as it is the radius. We need to know what the radius is. And that's going to be 5. Okay, that's the first part. So, we have this conical tank. The fact that it's a tank just means to hold a body of water. That's 10 feet across and 12 feet deep. If the water is flowing into the tank at a rate of 10 cubic feet per minute. So, water flowing in, remember, if you're not really sure what that is, look at the units. It tells you everything that's going on. Cubic feet, so that's volume. Right? In general, flowing in, flowing out, filling up, that's all volume. So that's what all this stuff is right here. It's the volume they gave us. So that's our given. dV dt, the rate of the volume, is 10 cubic feet per minute. So feet cubed per minute. What they want us to find. So let's see. Find the rate of change of the depth of water when the water is 8 feet. So the depth of water is how deep this water is in this tank. So like that. That's our depth of water. So they want us to find the rate of that guy. So our want is dH dt. So that's what we're wondering about. So the depth of the water when the water is 8 feet deep. So when it's happened to be 8 feet. Again, notice we talked about this before, but when is a keyword here. That means that this is a variable. It's not a constant. We can only plug this in after we take the derivative. Right, because they're saying, hey, when this water happens to be 8 feet deep, how fast is it rising? So you only plug that in after we take the derivative. Very important. When you see the words when, it means after the derivative. So when this happens to be 8 feet deep. Okay, so that's our given. That's our want. We have this conical tank here. So what we always do. We try to find the equation that kind of connects all this stuff. Now we're talking about the volume of a cone. So we have to do the volume of a cone. Volume of a cone is 1/3 because it's pointing to stab somebody. Area of the base times height. This is the volume of anything. And then our area of base here, we have a circle. So that's our base. So pi r squared. So our formula is really this. Volume equals 1/3 pi r squared times h. Now I know the next thing we normally do, right? We take a derivative and we plug stuff in. There's a problem here though. If I try to take a derivative of this, look what happens. I have two variables, r and h. First of all, it's a product rule, and we don't want to mess with that right now. Second of all, if you actually do it correctly, you're going to get dRdh, dRdt, sorry, and dHdt. I want dHdt. That's what I want. I want dVdt. I'm going to have that. I don't have dRdt anywhere. There's no radius at all in this problem. Well, there's no rate of the radius at all in this problem. So that's a problem. I cannot take a derivative with an r there because there's no dRdt anywhere. So we got to get rid of it. How do we do that? We use similar triangles. So we have to use similar triangles. So what two similar triangles are we going to use? Well, we're going to use the given. Right? They give us this whole thing here. We have this big triangle. You know the radius is 5 and the height is 12. When you have this smaller triangle, now a lot of people say, oh, isn't that 5 or 12? No, that's the water, right? I have no idea how big that water is. So all we're going to do is put an r here and put an h there. So this smaller triangle with r and h. And these are similar triangles. They share an angle, they share the sides, similar triangles. So we have to set the proportion, right? I always like to do small over big. So I'm going to do like r over 5 equals h over 12. And remember the whole point is that I want to get rid of that r. So I want to sub in for r. Because you want to take a derivative with no r there. So what we can do here is we're going to solve for r. So I'm going to cross multiply. I'm going to get 12r equals 5h. I'm going to get R equals 5h over 12. So that's my R. And what we're going to do is we're going to rewrite this with the R plugged in. So now I'm going to have this. Volume equals 1/3 pi 5h over 12 squared times h. That's my equation. And now you have no h's. No r, sorry. So now I could have everything I need. Let's simplify this first though before we start talking about it. Square goes to both sides. I get 1/3 pi 25h squared over 144 times h. Remember, h is always over 1, so we can simplify this a little bit more. So we're going to have volume equals. We're going to multiply the 3 times 144. I have no idea what that is, so that's 3 times 144. 12, 13, 432. Took me a little longer than it should have been. So I'm going to get 25 over 432. Let's add the pi in there also, because remember pi is always on top. Then look at my h's. H squared times h is h cubed. So that's my ugly, ugly volume formula. Right, that part was ugly. The rest part is to be easy. So I simplify this. I simplify my volume formula. I start off with this. I couldn't take a derivative of r because I have no dr dt anywhere, so I had to get rid of it. So I used similar triangles to figure out what r was. I subbed it in. Then I simplified this from algebra, and I got here. What do we do next? What we always do. Take a derivative with respect to t and plug stuff in. So derivative v is dv dt. Derivative of this is all just a number, right? That's all just a number. So derivative of this is bring the 3 down, subtract 1 off. So I'm going to get 3 times 25 pi over 432 h squared, wrong variable, dh dt. Now, I don't know why I multiplied the 3 times 144 since they're going to cancel out right now. So I get dv dt equals 25 pi. This is 144. I know that because I had multiplied it earlier. h squared dh dt. Right? And now I just got to plug stuff in. Right? What do I know? I know dv dt is 10. I know at the height when it's 8. I'm going to try to find dh dt. So, plug it in. This is 10. I get 25 pi times 144, 8 squared dh dt. Remember, 8 over 1, so you get 10 equals 64 times 25 pi over 144 dh dt. Divide by all this monstrosity, and you're going to get 10. Then multiply by reciprocal times 144 over 64 times 25 pi equals dh dt. You can type that into a calculator, get an ugly answer, dh dt. If we're worried about units, it is h over t. H is feet, and then t is minutes, right? It's not volume, so it's not cubed, it's not area, it's not squares, it's a normal side. So, what was it? Feet cubed, feet over minutes. And that's the idea.